In this lesson, I'll talk about the vector equation of a line and then show how to derive the parametric and Cartesian form of the equation of a line. The only thing you have to recall is that when two lines are parallel, one is a scalar multiple of the other. So if I have a line, this line AR, and that is parallel vector B, then it means that AR is some constant multiple of B. That is the idea we're going to use to derive the vector equation of a line. Now what it means is that if I want, from this diagram, we are in the Cartesian plane, the y and then the x axis. Now, if I want to move from the point O to the point R, the possibility is that I can move from OA and then from A to R. So let me denote this vector from O to R as this small vector, and then OA I denote it by A. So the steps, the first step is that we know that two lines are parallel. The line AR, or the vector AR in the Cartesian plane, is parallel to the vector B. Parallel lines, as we say, do not meet. So step one, we know that AR, the vector AR, is some constant multiple of B. So these two lines are parallel. The next thing is that we say the coordinates of A are A1 and A2. The coordinates of R are X and Y. And we have B is also equal to B1. This has already been written as a vector, a position vector. So I write it B2. Now, let me come up here. From the diagram, I denote OA, the vector OA in position vector form. I write it A1 and A2, and I have denoted it by A. OR is the vector from O to R, and that is X, Y. This point is any point on the line whose equation I want to find, and there is a known point on the line, and an arbitrary point R on the line. I can denote the line whose equation I want to find is line L. As earlier said, OR, if I want to move to from O to R, I can go through OA plus AR. Now look at the movement from O to R. I move from O to A and then A to R. Take note of the position of this and that. You see, it starts here and ends there. And then take note of the position of A and A. I move from O to A and I start from A to R. That is vector addition. So from here, OR, we have said that OR is equal to small r. Okay, so R is equal to, one form is R is equal to OA is we denoted by A plus AR. We have said that AR is equal to lambda B. So if we substitute, we have lambda B. And this is the vector equation of a line. So now we have one form of the vector equation of a line. The second thing I want to talk about is the parametric form. So I write it parametric form. So the parametric form for the, let me make space. For the parametric form, I write vector R in terms of its position vector. First, let me repeat the vector equation. Now we know the vector equation of the line is this. So in this form, I put X, Y in terms of position vector, and here I have A1, that is OA, A1 and A2 plus lambda B1 and B2. Let's not forget that lambda is in R is a real number. Lambda is a real number, a scalar, and it's a real number. So the parametric form of the equation of a line is obtained by equating x is equal to the first components. So we have x is equal to a1 plus lambda b1. Let's label this equation 1, and y equals a2 plus lambda b2. Let's label this equation 2. These two equations we call the parametric form of the equation of a line. Now, the last thing I'll talk about on this is the Cartesian form. The Cartesian form. Now, we obtain the Cartesian form from the parametric form. In equation 1, we can make lambda the subject, and equation 2, we also make lambda the subject. From equation 1, x is equal to a1 plus lambda b1. This is equation 1. Now, if we make lambda the subject, we have x minus a1 over b1. This is equal to lambda. From equation 2, we also obtain that y is equal to a2 plus lambda b2. From 2, we can say y minus a2 over b2. This is equal to lambda. Let's label these equations as equation 3 and equation 4. Because they are all equal to equation 3 and 4 are equal to lambda, we can equate equations 3 and 4. If we do that, we have x minus a1 over b1. This is equal to y minus a2 over b2. And this equation 5 is called the Cartesian form of the vector equation of a line. The Cartesian form of the vector equation of a line. Note that we have derived the vector equation for a line in 2D, and this is the vector equation. This is the vector equation, and we have derived the parametric form, and in addition we have derived the Cartesian form of the vector equation of a line. Now let's solve some examples on this. On screen is a question that says that a line passes through the point A, 1, 5. Its direction vector is, and I write 3, 2. That is the direction vector. Find the vector equation, the parametric equation, and the Cartesian equation. Now, to solve this, write solution to the problem. Now, the vector equation of a line is, as we have derived, is r a plus lambda b. These are vectors where lambda is in r. Let a be equal to oa, so that we can write the position vector as 1, 5, and b is equal to 3, 2. Right, vector r is equal to x, y, as we had on, this is an arbitrary point, and we use that to find the vector equation. We then have x, y is equal to 1, 5 plus lambda 3, 2. This is the A part of the question. A part of the question. The vector equation of the line. We can as well write it in this form: x, y is equal to 1 plus 3 lambda and 5 plus 2 lambda. This is also acceptable. B, the B part of the question. B, we are to write the parametric form of the equation of a line. The parametric form, as I described, is x is equal to 1 plus 3 lambda. That is equation 1. And the second one is y is equal to 5 plus 2 lambda. That is 2. This is the parametric form of the vector equation of a line. C, we are to write the Cartesian form, and we obtain the Cartesian form from the parametric form by making lambda the subject. So from equation 1, we note that x minus 1 over 3 is equal to lambda. Secondly, from equation 2, we note that y minus 5 over 2 is equal to lambda. Since these two equations are equal to lambda, we can equate them. So we say that x minus 1 over 3 is equal to y minus 5 over 2. This is the Cartesian form of the vector equation of a line. Now we can go ahead and cross multiply. Okay, this goes there, this goes there. We have 2 into x minus 1. This is equal to 3 into y minus 5. On expanding, we have 2x minus 2 is equal to 3y minus 15. This we can also write as 2x minus 3y. This is equal to minus 13. This is the Cartesian form of the equation of a line. If there's no restriction, you can also leave your answer in this form as the Cartesian equation of a line.